Da, 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 da. Look at this! Oh my god, I figured it out. It's the Great Pyramids tech. And this little video will be all about delta T. If you don't know what delta T is, I don't know. I think it's got something to do with the pyramids. And it's also a differential between two measured surface constants, i.e. hot and cold sides of a thermoelectric cooler, power electric generator. So what we're going to do is we're going to look at the Great Pyramid and what it was, what it looked like, what it is today. So today, I'm sure you're all familiar with the bent pyramid, which for years was they tried to say, oh hey, that bent pyramid, they just screwed up. They didn't know what they were doing. Wrong. The bent pyramid was a tribute pyramid to how the Great Pyramids looked before Xerxes' army tore off the outer limestone sheathing. And you look at it now and you're like, why did they leave that little piece on top? Because that wasn't part of the magic. Xerxes' armies went in and smashed Egypt's armies. They smashed the armies, and then they smashed the pyramids. They smashed the magic. And that was really what it was. It was the magic that surrounded the Great Pyramids. So what is the Great Pyramids? What are they? What are they? What are they? Everybody wants to know. They're giant heat sinks with massive surface area. So the mathematics behind what the Great Pyramid is, everybody says, oh, it's mystical, it's this, that, and that. What's that too? Sometimes. But this time, let's look at what it is compared to delta T technology. So the outer limestone sheathing that was over there was a heat shield. And in that heat shield, there was a bunch of holes, which are evident from the erosion patterns on the surface of the steps. You can look at them and compare it. And I'm not going to show you. You can go look at it for yourself. But anyway, so they had these pluggable holes on this outer heat shield over the core. Now, the core was constructed to be connected thermally to the bedrock. It was literally built onto the bedrock. They didn't just build it on the sand. They built it directly onto the bedrock. And that bedrock carried away the heat. So it's this giant heat sink going out into the desert, sinking that heat out. And then, of course, these giant blocks up here up on top, that was black basalt up here, these giant blocks up here, which some of them still exist to this day, because once you haul some black basalt from, 400 miles away, you might as well keep it around, right? It also signifies the fall of the Egyptian army. So this is an artist's rendition of what I think the pyramids looked like back then. And this would be for pretty much all the pyramids, small, big, everything. They all used to look like that. But Xerxes' armies of anti-masons destroyed any resemblance to the magic of Egypt. And the magic was they could produce water from air using an air well technology. Now, air well technology has been controversial. It works, but not very well. But we're going to look at why theirs works so well. If you can see the steps were the greatest surface area on the base, up to, and the pitch and everything, made it so that the thermal conductivity of the rock carried it away at a set rate. So they probably built smaller ones of these beforehand and put them all over the place. There was actually one which was a pyramid rock, which was interesting because there's this lake out in the middle of nowhere, and there's this thing that was just like, wow, why does that thing shaped like a pyramid? Well, you can imagine if they had one of these sheaths over it, and they had the humid air of the Nile Delta, Nile area, that humid air to the bedrock in that area is what you need. It's called dew point. The temperature differential between the outside air temperature and the bedrock temperature creates a connection for the dew point, meaning that if you got something at exactly that temperature that had good heat conductivity, you'd be able to pull moisture right out of the air. And that's exactly what the Great Pyramids did. So they had, around the Great Pyramids, they found bread factories. And, bread factories, huh? Hundreds of bread factories and beer factories. Well, what do you need for beer and bread? Water. Lots and lots and lots of clean water. So I put my archaeologist hat on today so I could talk a little bit about this and why that affects us today. Why is the technology of water from the air so important in today's world? We are out of water, folks. The water's not coming from the sky in big amounts. We got to start water farming like the water farmers on Tatooine. We got to start upping our technology game so we can survive as a species. Because believe it or not, we can be wiped out. Poof! If the water stopped, we'd be totally screwed. So we got to start thinking about how to collect that water from the air in places that we like to live. One of those things we can do is we can follow the Great Pyramids technology, and we can take this one I call the Alamosa water tree. The Alamosa water tree is just a big plastic hollow tube tree, and it can look like a big spaghetti noodle octopus, as long as all the things are hollow and they're all open. And eventually you might want to put little pivoting things, but they just have to be open. And what happens is when the wind blows, it creates suction on this hollow trunk. And that hollow trunk is attached to this foam heat shield here that goes over a big boulder, say in a rock garden. Or it can also be a rock face, like a rock face that's sticking up. So what you do is you take this foam heat shield, throw it down over some aluminum wool. And that aluminum wool should be of a certain density and grade so that when it's damp or even in contact with the rock face or the big boulder that's sitting down underneath the foam heat shield, that it conducts heat or conducts cold and conducts heat to the rock, but it basically makes a little air conditioned area where humid air, as the wind blows gently in the mornings or all day long or whatever, as the wind blows and sucks, it pulls air around the bottom of this foam heat shield, around the skirt, through the aluminum wool, and then the aluminum wool collects the water from the air into a holding basin. And of course you can take the holding basin water, you can either seal it or you can make it so it's distributed out into a garden. Now in this particular drawing here, you see I put a heat sink spike. This would be like if you just take a great big boulder sitting in a garden, you drill a big hole or multiple holes through it and put heat sinks down as far as you can go so you can get that heat down there. And that heat sink spike's probably going to be made out of aluminum. Although aluminum corrodes in the ground, you might want to coat it with something. You know, you can plate aluminum with other metals that'll be more resistant to being in the ground, like copper, for example. Copper doesn't last forever either, about 30 years. So either way, you want that thermal conductivity of the aluminum, and you want the protection of like a layer of copper or a layer of another metal that won't interfere too much with the thermal conductivity to the surrounding bedrock or soil. And of course you're going to want to use a cement of some kind, usually I suppose. In this case, you don't necessarily have to. You probably just have to beat it into the ground with a giant spike hammer. Bang, bang, bang. Unless this is rock, then you have to drill it out and then set it with some epoxy or some thermal cement. Okay, so this design right here is interesting. This one I discovered when studying lichen, high altitude lichen on rocks. And I looked at the way the air pores were on the lichen and the fibrous protein materials that make up the inner strands of the lichen, and the way the outer, it has a heat shield that has almost the same configuration as this. And right about the same time, I ran across that. So the Great Pyramid literally is based on, the technology is based on lichen. If you studied lichen enough, you would figure out that the lichen, way up near the tree line, or even above the tree line in some cases, is able to collect water from the clouds, from the air, because of the delta T, which causes the water to collect onto the micro, almost scopic strands of the lichen fibrous internals. So, you know, you can get more than just water, though. As you can see, I'm sure you're all looking over at this. What is that thing? What is that thing? Ah! Okay, this is a thermoelectric array. And this one would be, you'd have a battery system, you'd have thermoelectric chips, and what you do one of two things. You can either have a fan that's powered by the thermoelectrics, or you can just have one of these cone-shaped windmill acceleration things, and it's basically just a big cone that's set on an axis like one of those weather vanes. So it's a coned weather vane, and what it does is, as the wind blows, it sucks air through this thing. So the faster you're going to suck air through here, you're going to have a rate. There's going to be a maximum rate because you're doing it. But if you drill down or dig down far enough to where the bedrock to soil layer is, you probably want to dig down. So this is going to be like for residential. So you're going to dig a pit or two pits. And this doesn't need to be rigid. It can be in segments and stuff. The main thing is that you put hot filtered air in one side, and you pull out this. It's actually cooled air, so it'd be cooled to ground. You could actually take that air and pull it into your house. So this is kind of like a free air conditioner that gives you free power too. Darn right. I know nobody wants free power and free air conditioning in the desert, right? That'd be, who wants that? So what you're gonna have to do though is you're gonna have to take copper tubing and bury it down in between the soil layer and set it right on top of the bedrock or whatever the hard pack stuff is, something that can carry away that heat. And you're going to probably need a lot of it, so you're essentially burying a bunch of copper in the ground, but it's for a reason. Now, could you do it with plastic? Yes, you can. There's thermal conductivities of plastics. Polyaniline black, I think, is one of the highest thermal conductivity, and then there's a high density, what is it, PEC. You can use PEC tubing. So let's just go ahead and use PEC tubing. We're going to have to use a lot more than copper to use PEC tubing. If you want more efficiency, you're going to probably want to use copper, but if you want something that basically lasts forever, you're probably going to want to use PEC tubing. So PEC tubing, PECs. And then what that does is you have a little pump in here, and it pumps the hot air, because you have to have a heat exchanger up here too. And you could have panels up there too that this doesn't have to be this configuration. You can have panels too. What you really want is an exchange layer. I just drew this one as a tube. You could do it as flat panels if you wanted to. That'd probably be way more efficient. I'm just drawing this as a tube just to get it out of the way. But this one just uses air, hot air. So you'd use hot desert air. And what it does is it has the temperature differential. Now this is only going to work in some places where it's hot on the surface and cooler on the ground. There's going to be a delta T. And I think it needs to be at least 15 degrees delta T for the thermoelectrics to produce like the highest amount. But of course, the hotter you get, typically, the better they work. So that's to get free power and free air conditioning in the desert. So that's pretty good too. And who knows? Maybe the Egyptians piped that off into their palaces, but most likely they just vented it out, because these big blocks can be found around Cairo in some of the religious buildings where they worship around those blocks. As far as I know, that's where the black basalt came from, because somebody had to pay to get that black basalt into town. So those were in the ruins of Memphis before it was called Cairo. Anyway, so this is pretty easy. Let's just go ahead and go over it real quick. We have the hot, humid air in of the Nile. Now these sit up on top of a hill too, and that was one thing that caught my attention. They put the Great Pyramids up on top of this point up above. It's like on like a plateau, right? And the wind always blew up there, and I think it was just high enough and just close enough to the Nile Delta, or the Nile Valley there, to where you get that humid air. And I mean, it's humid there. If you've ever been there, it's humid, it's muggy. And the bedrock temperature there is at dew point temperature almost year round. So this technology, since the cores are still there, here's the fun part. You could rebuild those and they would work. Now, how would they work? You know, remember I had the pool underneath, and they had these little weird things that had like little tubes and stuff going through the pyramid. Well, I think that you have to wet the structure with water against the bedrock. So it's kind of like thermal paste. You're using the water that it collects from the air, and you could probably put water in there to start the process. But if it was dry, it probably wouldn't work. So you're going to need to wet the bricks. The bricks need to stay wet up to a certain level. If you're going to create that thermal transfer, you need to have it wet up to a certain level and just kind of like recycle. So it's definitely a vision of perfection. They really thought about that for a long, long time. Ancient Egyptian engineers, they thought it out. It was awesome. What a bunch of geniuses. Okay, but that's similar to how the lichen method works, and this is the Alamosa water tree employing hollow tubes, foam heat shield, high surface area heat exchanger, aluminum wool. It's called aluminum wool. I'm not sure if you've ever seen aluminum wool, but it's kind of cool stuff. You can buy it in big matted sheets, and that's going to be the future of gardening and agriculture in the Alamosa, Colorado area. I spoke with a Native American, or Indian, as some people call him. This guy, he was a teacher, and he said, "Zio, if you can bring water to Alamosa, man, that would be great." So I did. This is the Alamosa water tree. It will provide as much water as any gardener would possibly need, and it actually goes even further. If you look over here, this is industrial. This is expensive. You're going to have to probably guard these because people will go up and chop them down and take all the metal. Okay, these are very expensive compared to the Alamosa water tree, which anybody could make. Anybody could make. It's cheap plastic tubing. You could literally make this in your garden tomorrow. It's just you don't even need the spike. You just need a big boulder that likes to sweat in the morning, so it's of the right density and has enough depth in the soil, and you'll get free water from that thing every single day. forever. These are industrial. And why I say industrial? Because you're going to have some investment. First off, these ones you're going to have to drill into the rock face. Now, looking at Colorado is where these things will work. And it's just straight up. You need a ground temperature of a certain temperature, and you need a air temperature of a certain temperature, and that differential creates the delta T. So, and you have that there. Now, admittedly, there's a lot of rain shadows. Alamosa is in a rain shadow, so you don't get very much there, but there are places where you can. And in some of the valleys where you have fog in the morning, this thing will work great in the fog. This thing will work even better. Okay, this uses an aluminum, just an aluminum spike, like that big around, a great big aluminum spike. And you drill it down, you drill a hole in the side of the rock, and then you thermal compound it or thermal cement it in, and then you bolt it to these wire wound aluminum copper trees. And these trees have a pitch and a length to the little arms. You can almost call them water needles, I guess. And they interact with the air. And as the air flies by 24 hours a day, 7 days a week. Now, you think about this, though. This is missing something, isn't it? What is that missing that these have? The heat shield. That's right. So on these right here, you don't have the heat shield. I don't necessarily think you'd want to forget that. But how are you going to get the air to go through there? So you could add a heat shield to it, but it's going to be, you're going to have to follow the Egyptian methodology, I think, because you don't have the same type of device at all. So in some places, I think that these would work best on the north side without, I don't even think I'd put a heat shield on them, on the north side, the shadow side of a mountain, which is moist anyways. You already have a moisture pocket there. And then, of course, the air blowing by all year long. Except for now, in winter, these aren't going to work at all. They're going to completely freeze up, and you're probably going to want to have this cone on them so the snow doesn't snap them off. Otherwise, they'll just be a giant... They're going to be the first things to freeze. They're going to be just basically a big frozen block of water. And that's going to be most of the year. This too, even in Alamosa, there'll be parts of the year when this won't work. Okay, and there'll be parts of the year where this won't work. Okay, there's certain places even though Colorado has ideal temperatures for the bedrock temperature versus the air temperature, and it has the right humidity and it has all of these factors, they're not going to work year round. So what these technologies will bring, though, is another layer, a percentage of water, and bring them to America. Bring them to Colorado. Bring them to the farmers. Bring them to the people that need them. That way they can have them. And this right here, if you've ever lived in Colorado, the best places to live in Colorado don't have any power. They don't have any water. They don't have any air conditioning. Now, a lot of times you don't need it, but most of the time, you know, that comfort, the creature comforts like the internet and things like that, you're going to want those. You're going to need those. And so this type of device here, or this type of technology, is definitely going to provide that. And if we take and we learn from this, we can also say that this is just one step in that direction where you can have power and air conditioning. And technically you could have water too. I mean, this probably would have an output of water. So, you know, you just put a little water tank there and you'll get water, power, and air conditioning from this. So this is the water horse. This will carry us into the future. And this one's really cool because it kind of looks like a horse too, right? So this one we're just going to call it a water horse. Or I guess we could call it, this is a desert version. Yeah, I like it. It's a water horse. But it's a water power horse. It's the powerful water horse. Oh, we'll just leave it like that. It's my horse. This is a techno horse, and this is the Alamosa water tree, and it's a robotic kind of tree in a way, and I don't know how long this is going to last in this current configuration, but these are great ideas. Now, we almost forgot about the little guy up there. What about the little guy? Come on, Zio, what's that over there? These are called water noodles. Water noodles. Very simple to make. You have a copper steel with copper coated. It's just got to be thermally conductive. It doesn't have to be super thermally conductive because it doesn't really produce that much water. And then you have a little tube that is either stamped against it or soldered onto it, so you have thermal conductivity. And you take these and you put them in the base, around the base of your plant, and then when the wind blows and there's humidity in the air, it collects the water and drips it right down into the root system of your plant, which is amazing. So if any of you are out there and doing some remote gardening, there you go. That's what you need. You need a water noodle. You need about, I'd say probably about 6 to 10 per plant, whatever plant that would be, and that should water your remote plants quite well at different parts of the year. I'm not going to say it's 100%. I'm going to say it will assist you. And there's going to be some places you're going to look for where the mists kind of like inhabit an area in the morning. And of course, that mist burns off every day, but every day there's like mist. So it would be like near a water source, but not necessarily. See, it's really hard to get rights right now for water. And until they make an air law that you can't collect water from the air, then we can use this technology. Right now, there aren't any laws. There's none. And right now, that means that these can be used, they can be used anywhere. And you'll be able to have, this one's really cool because this one produces water, power, air conditioning. I mean, what more could you want? So this is like move to Colorado and build some of those. So I think this is going to be the future right here. That is the past, hence the archaeology hat. All right, well, I'm about done with my video here, and it's pretty exciting. I would love to sit here and talk about every aspect on the board, but you know what? You can read. At least you should be able to. If you can't, well, I suppose I'll read it to you. Well, this one here is, you know what it is. I just told you what it was. All right, so hope you enjoyed the video. Smash that like button, subscribe, share the video, share the video, share the video, share the video, share the video. This is for the world. This is the world technology. The Egyptians left us the technology to look at. Xerxes' army, I guess, they just weren't dedicated enough to tear those pyramids all the way to the ground. And they're never going to be able to either. So they will always be that marker that some genius is always going to figure out. I know what those are. They're gonna find out the delta T. The delta T between the air and the ground at the side of the pyramids is perfect for an air well. I bet that's what those were. And there's this other guy, I saw him on YouTube, and he said the internal makeup of the Great Pyramid was a giant pulse pump. And everybody's like, why would you want a giant pulse pump way up there on the top of a hill? You know, that guy there, I was like, huh. So if you type in water and you type in pyramid, Great Pyramid, you'll find his video. But this is why there was water there. This would be water forever, and it'd be clean water too. Really clean, because over those steps, it would be like sand-filtered water. Can you imagine drinking sand-filtered water, or making bread and beer with sand-filtered water thousands of years ago? Everybody would want it. So the Egyptians had an empire. It was a water empire in the desert, and that is the main reason why they're still there today, is because the foundation was laid. This works, this works, this works. That is what you should be thinking about. Delta T technology. This is just an idea. These are just my ideas that I'm sharing with you. We're taking them and we're throwing them out there in the world because you know what? One man cannot do all of this. Cannot. You just can't. I need your help. I need your help to bring this technology to market. I need your help to realize the potential of the Alamosa water tree. I need you to realize that I need your help here on this planet in this lifetime as soon as you can. So let's go ahead and get these things to market as fast as possible. Tune in, subscribe, smash the like button, comment, comment, comment. Tell your friends, share this video with people so people can have water. Okay? Because we're going to have to start farming the water. We just can't just wait for it to fall out of the sky and pull it out of wells, because it's just not coming now. It's not coming like it used to. It's not out there. The clouds just were non-existent this year. And admittedly, we're going into a dry cycle now, but if you look at the drought right now, August 2022, the drought. This is just the beginning of the sun's hot cycle. So we're in for a real dry spell. We should be building reservoirs, and we got to find some way to fill them. We got to find some way to fill those reservoirs. And this is industrial technology. It can be done. We can pull that water out of the air and fill up reservoirs. We can create brand new reservoirs all over, especially in Colorado. Colorado is the place to be. Just do it. 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 I'm excited, but all right. Well, this is Zeo205 signing off. Later.